Good day. In this video, I'm going to solve an electrodynamics problem, and that electrodynamics problem is the problem of scattering by a conducting sphere. Okay, so we have a sphere, and it's made of conducting material, and we send in some incident light. Okay, and that's a wave which oscillates. Okay, and the scattering process we're going to go by is the following: that this incident light, which has an also a magnetic field, it's going to give rise to so these incident fields, they give rise to an oscillating dipole and magnetic dipole moment in the sphere. Okay, and these guys, these oscillating dipoles, they give us the scattered radiation. Okay, and what we're going to be interested in is the differential scattering cross section. Which I'm going to define as r squared times the square, so I can define it like this, divided by E inc rather. So the square modulus of these two. So the square of the scattered electric field divided by the square of the incident electric field. Okay, and I'm going to take E incident to be of the form some polarization direction, some magnitude E0. Okay, and then I can attach another formula, but that's not going to matter much. So e to the I k0 dot r minus omega t, if you want. And then I'm going to say, I'm going to take the incident magnetic field to be n0 cross E0, E in incident, okay? And epsilon 0 is the polarization, okay, of the incident wave, and then n0 is the propagation direction. Okay, so our first task is to determine that when we have, well, actually I should emphasize also that we are in the long wavelength limit, and in this long wavelength limit, we can actually assume that these moments, this electric dipole and electric magnetic dipole moments, they are as if this sphere was under a homogeneous magnetic field, or electric and magnetic field. Okay, so that's actually a rather easy electrostatics problems that we have to solve, but we have to do it for the case of a perfect conductor. Okay, and we're going to do that first. That's asked in the question. Okay, and then we're going to put the scattering stuff together, which I've already specified. Okay, and let me say also that in this scattering, in this differential scattering cross section, we're going to separate the components which are in the plane of incidence of the waves. Okay, so, and what that means is you have some incoming wave which has a propagation direction n0, and here's your sphere, let's say, and you're going to have some outgoing wave which has a propagation direction n, and this forms a plane. And it turns out that the polarization we can take to be in plane or out of plane, and we're going to calculate the differential cross sections for each of those components. Okay, I'm going to discuss this in more detail when I'm doing it. Okay, and that actually also allows us to determine the polarization of the scattering. Okay, so I will define all of those terms this is enough for now, because the first thing I will concentrate on is calculating the dipole and magnetic electric and magnetic dipole moments of this sphere. Okay, so so let us start. So basically, what I want to first discuss briefly is, so what happens, what dipole moment does a sphere have when it's in a constant field? Okay, so let's say E0 is E0, and let's have it point in the Z direction. Okay, so let's solve this electrostatics problem first. And you know that what you can do, I'm going to solve the following problem to start with. I'm going to assume that outside we have vacuum, and inside we have material with a dielectric permittivity of epsilon. But then for the ideal conductor, I'm going to take the limit of epsilon going to infinity. Okay, so let's do that quickly. Well, I'm going to do that a little bit quickly, because I'm going to take the scalar potential to be of the form A1 r cosine theta and B1 over r squared cosine theta. Okay, and I'm going to here make one little leap, that this is the field at large distances. So this potential is, of course, a different form depending on whether we are inside or outside the sphere, and r, capital R, is the radius of the sphere. Okay, so let that be our starting point. Okay, and this already has the right behavior at r going to infinity, because it just gives us the electric field. Okay, so first we're going to make sure that this potential is continuous. So A1r is equal to B1 over r squared, so that r equals r. That's where we apply the continuity condition, is E0r. So B1 is equal to A1 plus E0r cubed. Okay, so that's one result that we have. And then we want to solve for A1. And how do we do that? So first let me actually just rewrite this result. So I have my new potential phi r theta, and that's A1r cosine theta. And here I will have A1 plus E0 capital R cubed divided by r squared cosine theta minus E0r cosine theta. This is valid. The first part is valid for inside the sphere, and this one is valid outside the sphere. And the next thing that we're going to do is to say that what we know is that there are no free charges around. So the divergence of the zero, this is a little bit of a reminder, okay? So the radial component is continuous of the displacement vector, but it doesn't, of course, the d in general is epsilon, whatever epsilon you have, times E. So this is not continuous, because the dielectric constant is different inside, depending on whether we are inside or outside. So let's just quickly finish this. So we're going to have, I'm going to take the derivative of the potential. Okay, so let's take the derivative of the potential. That's A1 cosine theta minus A1 plus E0 r cubed divided by r cubed minus 2, actually. This is minus 2. There's a 2 there. And here there's a cosine theta, of course, and then I have minus E0 cosine theta. And then I can say that epsilon times A1 is minus 2 epsilon 0 A1 plus E0 minus epsilon 0 E0. So this is actually the equation that will determine A1. Okay, and so basically we're going to have epsilon A1 is equal to minus 3 epsilon 0 E0, and then what? Minus 2 epsilon 0 A1. So that makes A1, sorry, I'm being a little bit too detailed on this one perhaps. just bear with me, epsilon plus 2 epsilon 0 E0. So that's a good starting point. This actually means, so this means that our, let's say, well, we can say what our electric field is, for example, right? Based on this one. So we can say that the electric field is actually negative of this gradient, okay? So the electric field is going to be basically this coefficient, really, okay? So basically E inside, which actually is the incident wave, has to equal no, sorry, that's E inside the E. That's actually the electric field in the Z direction. Let me write this again. So E inside the sphere is actually 3 epsilon 0 epsilon plus 2 epsilon 0 E0. Okay, yeah, that's right. And let's just go back to our studies of dielectrics for a minute. So basically, we have that divergence of E is rho over epsilon 0, which is actually the free charge over epsilon 0 plus the bound charge, but the bound charge we can write in terms of the polarization. Okay. Well, basically, I'm just what I'm after is the polarization in terms of the electric field. Okay, but this actually tells me that epsilon 0 E is equal to D minus P, from which we get that D is equal to epsilon 0 E plus P. Okay, and what we want is also to use the fact that the polarization P is epsilon 0 dielectric constant times the electric field in a linear material. Okay, so basically what we have is D is equal to epsilon 0 1 plus chi E times E in a linear material. Okay, and this whole thing is epsilon. Okay, and so now we can immediately write here one thing, that so basically the polarization is going to be this electric field times epsilon 0 chi E. Okay, and I just want to get what chi is. So we have that epsilon is equal to epsilon 0 plus epsilon 0 chi E. So epsilon 0 chi E is epsilon minus epsilon 0. Okay, and then we can just use that because polarization is epsilon 0 chi E times E, and we already have E. So basically what we're going to get for the polarization is epsilon minus epsilon 0 times 3 epsilon 0 divided by epsilon plus 2 epsilon 0 times E0. And that E0, of course, is going to be our incident wave. Okay, and now let us take the limit of epsilon going to infinity, which is valid for a conductor. So the polarization per unit volume is actually P is equal to, what is this? 3 epsilon 0 E0, okay? But we want not the polarization, but the dipole moment, which is just the polarization times the volume of the sphere. Okay, so the dipole moment, this is capital P, this is lowercase p, apologies, is 4 pi epsilon 0 times r cubed E0. Okay, so that's one part of the problem, is to find this. Okay, that's part A of the problem. And now we want to do also the magnetic field. Okay, so we also have the, I'm not going to repeat that because basically you can also do the following, right? So you can actually take another problem similar to this one, where you take a sphere, assume that it has permeability mu. Outside we have permeability mu 0, because outside we have vacuum, and we assume that there's a magnetic field, or let's say H0 in the z direction, okay? And then we solve this by the magnetic scalar. Sorry about this. This is H0, so there's a magnetic field in the z direction, um, um, and so basically we can go and solve this with the same technique, and of course we're going to get very similar results, because what we're going to get is that the H field inside the sphere is going to be 3 mu 0 divided by mu plus 2 mu 0 H0. Okay, so that's exactly analogous to the previous case. However, now we have to consider um, that it's a perfect conductor. Okay, and the perfect conductor is actually a superconductor, you could say, is a perfect diamagnet. Okay, but first we want to calculate the magnetization as a function of the sphere, given that it has this magnetic field. Okay, and I'm going to so just go back to magnetostatics now. Okay, so sorry, what is this? Sorry, how does it work? Curl of B is mu 0 J free plus mu 0 bound current, but bound current we can write as the curl of the magnetization. And here, this part we can write as mu 0 curl of H. Okay, so what we're going to have is that B is equal to mu 0 H plus M, apparently, and M is equal to magnetization times, susceptibility times H, okay? So we can say that B is mu 0, 1 plus chi M times H, okay? And this whole thing is, so this is actually the definition of the of mu. Okay, so the magnetic permeability, and so basically from this it follows that mu minus mu 0 is equal to mu 0 chi m, it seems. Okay, so then we go back, and we have this relation here. Okay, so basically what we want here is that m is equal to, well, chi m, which is mu minus mu 0 divided by mu 0, and then 3 mu 0 divided by mu plus 2 mu 0 times h0. Okay, and then the mu 0, these cancel. But the important thing is that in a diamagnet, mu actually goes to 0. Right, so chi m or another way to say it is chi m in a perfect diamagnet is -1. Okay, so as a result, the mu's will be 0, and what we get here is that m is equal to minus, what is this? Mu is 0, so we get minus. It seems that we get minus h0 divided by 2. Okay, now I feel that I'm actually, I might have one little problem here. No, but okay, I guess it's okay. So, okay, sorry, I forgot the 3. Okay, so I forgot the 3, okay. But then what we can do, also, I will use the fact that H0 is mu 0 B0. Okay, so I will write this in terms of B0 over 2. But the other important thing that I will do is I will express the magnetic dipole moment, okay? And that magnetic dipole moment ends up being minus 2 pi r cubed mu 0 B0. So that's where we're at. That's where we are at, okay? And now, actually, I'm going to do something else. I'm going to here, and I apologize for this, but I found this much easier to do in these units. But I'm going to go over to the CGS units that are used in Jackson. Okay, so I'm going to say from now on that P is R cubed E incident, whereas M is actually minus R cubed over 2B incident. Okay, this is consistent with the results that we found. Okay, so it's all consistent with this and this. Okay, because now I'm going to go back. So we did the electrostatics and magnetostatics that were necessary to solve this problem. The next step is to go and do the scattering. Okay, so the next step is to study the scattering. Okay, so I said, I might not have said this, but actually well, the scattering electric field has the form k squared e to the I k r divided by r n cross p cross n but there's another term which has to do with the magnetic field, which is minus n cross m. Okay, so that's a result that we know from previous studies. Actually, I derived this one in the previous problem. This one is also in Jackson, but I will leave it as the derivation aside for now. And then, of course, B scattered, I'm going to take that to be n cross E scattered. Yeah. Okay. So this demonstrates how to put together this scattering problem. From the incident fields, we get the P and M, the dipoles, which determine the radiation. This is, of course, a spherical wave that's spreading out in the radial direction. Okay, so that's what we start with. Okay, and so let's do our substitutions. So we're going to have that the scattered wave is k squared e to the I k r divided by r. And here I'm going to have, well, I'm going to write, let's say, I'm going to write n cross epsilon 0. That's the polarization of the incident wave. N minus n cross, well, actually, for this m, we know that, okay, we know the following, that, so this is proportional to B incident, but we know that B incident is N0 cross E incident. Okay, so this is going to be N0 cross epsilon 0. I'm going to divide it by 2 because I see that, and I'm going to also change the sign because there's a minus sign and there's a 2 here. Okay, and I'm going to put my r cubed outside. Okay, so I was using, what I was using here is two things, that the incident wave is some polarization times E0, okay, and that the incident magnetic field is N0 cross E incident. Okay, so I was using these two. So this is, of course, N0 cross epsilon 0 times E0. Okay, so that's actually what we're going to start with, and then we're going to actually massage this or sort of expand it all out. Okay, and I prefer to write it because I'm just used to the back cab rule in a particular way, as e to the I k r over r minus n cross epsilon 0 minus 1/2, or plus actually, cross N0 cross epsilon 0. That's a vector. Okay, and I could put my r cubed wherever I want. Okay, so now let's work this out a little. This is just two double cross products. So I'm going to rewrite my scattered field as, so k squared e to the I k r over r big R cubed, and I have n dot epsilon 0 minus epsilon 0 itself, okay, plus I have n0 over 2, I guess, n0 epsilon 0 dot n. I don't have space here, so I will write it here, minus epsilon 0 over 2 n dot n0. Okay, so let me rearrange this. So scattered electric field, k squared e to the I k r divided by r cubed. And if I rearrange this, I'm going to have it, it seems, sorry, this is minus, this is plus. Apologies, because I put a minus sign here. So I'm going to have here epsilon 0, 1 minus n dot n0 divided by 2. Okay, so that's the start. And then, so I actually put these two terms together, but I can also put these two terms together as, let's say, minus n minus n0 over 2 epsilon 0 dot n. Okay, so that's actually our scattered electric field. Okay, and now we remind ourselves what is the differential cross section. So d sigma d omega is actually, it's going to depend on the square. Okay, so it's actually r squared is this thing squared, modulo squared, divided by E incident squared. And sorry, actually, I lost something. Sorry, I apologize. I go back here, but I lost the E0. So all of this should have had an E0 here. But that actually doesn't matter because in the end it's going to cancel. But it's better to keep things around which are there. Okay, so this E0 is just the correction. Okay, so the first thing that we're going to need for this, of course, is the square of ESC. Okay, so let me write it cleanly what ESC is. K squared e to the I k r divided by r E0 r cubed E0 1 minus n dot n 0 divided by 2. Okay, minus n minus n0 over 2 epsilon 0 dot n. Okay, so that's what we have, and now we want to square this. Okay, and then we're going to analyze it, make some sort of angular analysis on it. Okay, so I'm going to square it first. Okay, well, if I go back here, I'm going to get the terms of the following type. I have to square this. Epsilon 0 squared, well, that's just a unit vector. It's the polarization direction, that's a unit vector. And then I have to square this also. So, well, actually, sorry, I should not forget these terms. So let's just get those things out of the way. So those are going to be k squared. And of course, one of them has to be complex conjugated. E0 squared r cubed divided by r squared. And the only thing that in the end, we of course need the differential cross section. All that's going to do once we figure this out is to get rid of the E0 squared and the r squared. Okay, so so the first term in this square, so I'm now going back to squaring this term. Epsilon 0 dot epsilon 0 is a 1, and then I have 1 minus this thing squared. So 1 minus n dot n0 over 2 squared. Okay, and then actually, let me square this term now and then do the cross terms later. If I square this term, okay, so I'm going to have a plus epsilon 0 dot n squared for sure. Okay, but I have to also square this vector that's multiplying that coefficient. So it's going to be n by n. Okay, so that gives me a 1. Then it's going to be n dot n0, so minus n dot n0 over 2, but taken twice. So it's minus n dot n0. Okay, and then in the end, I will also have a plus 1/4. Okay, and then I also have the cross term, and the cross term is going to be twice. We should note one thing, that epsilon 0 is a polarization direction, n0 is the propagation direction of that same wave. Okay, so that actually that epsilon 0 times this is actually 0. So what that's going to be is twice 1 minus n dot n0 over 2 epsilon 0 dot n squared. Okay, so that's but we're not done yet, because actually we can make a further simplification, namely that we have here epsilon 0 dot n squared. Here we also have that, and then n dot n0, and this is sorry, this is of course minus, because it's a plus term multiplied by a minus term. Okay, so that cross term is a minus, and we see that this cancels this. Okay, so let's write this e squared as k squared e0 squared r to the 6th, r to the 6th. And is it k squared? No. Oh my god, I'm so sorry. This is k to the 4th. K to the 4th divided by r squared. Apologies. Okay, anyway, so I'm going to have here 1 minus n dot n0 over 2 squared. And here I have what? So the 1 plus 1/4, that's 5/4 times this, but minus 2. So I'm going to have a minus 3/4 epsilon 0 n squared. Okay, so that's my final result. Okay, and now I'm going to write a provisory differential scattering cross-section as k to the 4th e0 squared r to the 6th. Now, no, without that, actually, so it's k to the 4th r squared, 1 minus n dot n0 over 2 squared minus 3/4 epsilon 0 dot n squared. And the interesting thing now is that we can actually break this down into two contributions. Okay, so we can break this down to two contributions. So suppose that I have n0 incident wave coming in like this, and n going out in that direction. Okay, and I'm going to call the angle between them theta. Okay, so then I can rewrite n dot n0 as cosine theta. And if we have that epsilon 0, the polarization is on this plane, then it also has to be that, well, n0 and epsilon 0 are of course perpendicular to each other, but in that case we will also have that epsilon 0 dot n0 is sine theta. Okay, so, no, sorry, no, that's 0 of course, but epsilon 0 dot n is equal to sine theta. Okay, because they are in the same plane, and n0 and epsilon 0 are perpendicular to each other. So in this case, when the polarization is parallel to the plane, to the scattering plane, then you have a differential cross section, which is k to the fourth r to the sixth 1 minus cosine theta over 2 squared minus 3/4 sine squared theta. Okay, then you can actually turn this into a simpler form, k to the fourth r to the sixth 1 minus cosine theta plus cosine squared theta over 4 minus 3/4 sine squared theta. And we can actually add 3/4 sine squared cosine squared theta and subtract 3/4 cosine squared theta to this. So that's going to make k to the fourth r to the sixth 1 minus cosine theta. And what did you do? Add 3/4. So that's actually plus cosine squared theta because we added 3/4. But we have minus 3/4 because we also subtracted 3/4 cosine squared theta. So we're going to have k to the fourth r to the sixth 1 over 4 minus cosine theta plus cosine squared theta. And so that we can actually reduce to k to the fourth r6 cosine theta minus 1/2 squared. So that's the parallel contribution. For the perpendicular contribution, all we have to see is that epsilon 0 dot n is actually 0. Okay, so that's all we need for the perpendicular contribution, which actually makes a differential scattering cross section in that case to be 1 minus cosine theta over 2 squared. Okay, so we have these two expressions depending on whether the direction of polarization is parallel to the plane of incidence or perpendicular to it. And what you can actually calculate, and you're asked to calculate this in the problem, is the polarization. And I just give you the formula. So it's d sigma d omega parallel minus d sigma perpendicular d omega divided by d sigma parallel plus d sigma perpendicular. Okay, so that actually wraps up this problem. Thank you for your attention.